All right. So morning, everyone. Let's continue our discussion. So basically, I'm planning that this class, we're going to finish reviewing the chemical concepts. And then after this class, we should be able to proceed to the next topic about the mass balance, energy balance. Okay. So regarding the reading assignment, it's the same as last time. So if you haven't finished reading all of the contents yet, you can also use this time to finish it up. Okay. So before we review more things, let's do a quick recap again. So if you recall what we learned last Wednesday, so basically we briefly went through how to balance the equations, balance the chemical reactions. So there are some simple ones like the reactions involving ions, right? Ionic species, or just simple elemental reactions, right? So you have iron reacting with oxygen to form iron oxide. So you can just count the elements, but there are some complex ones where we have to use some tricks, right? So we need to look for the unique elements and then list up the equations to basically balance the numbers, right? So then we introduced what are mole, molar weight, and molarity. Mole is basically a number of molecules, a number of atoms, right? 6.02 multiplied by 10 to the 23rd. And then we have the molar weight. It's just the molecular weight that has the unit of gram per mole. And then also the molarity. So it's just a simple way of showing, of saying mole per liter. Okay, so molarity is generally shown with the unit of M here. So we spent quite a lot of time talking about the chemical equilibrium. So in general, chemical equilibrium determines what is the final state of certain reaction because there's not a reaction that can occur completely, right? So we have the general form is AA plus BB going to CC plus DD, right? So we define this equilibrium constant, which we can use that to calculate what is the final concentration for all of the species, right? So more specifically, we mentioned that there are three applications of the equilibrium constant. So we have the solubility product, which determines the solubility of any solid, right? So although rock has the shape of the rock, but it also dissolves in water. So for example, the calcium carbonate can dissolve in water to form calcium ions and carbonate ions. So according to the definition of the equilibrium constant, so we have the concentration of calcium multiplied by the concentration carbonate, right? And then divide these concentrations by the concentration of the calcium carbonate. But we also mentioned that for solid, liquid, or gas species, their term, basically the x over x is 1, right? So that's why for this equation or for this chemical reaction here, then the equilibrium constant is just the product of these two ions. So we call this basically the equilibrium constant for these dissolution reaction as the solubility product, right? So it's KSP, solubility product. So we found that generally, because these reactions don't happen in a large extent, so only a tiny fraction of the solid can get dissolved. So their value is very small, right? 10 to the negative 8.34. So that's why for simplicity, we defined a parameter or the calculator that's called the P, lowercase p. So lowercase p, let's say of a K, is just negative of log 10 of K, right? So we can basically write it out as, let's say, PKS or PKSP. For this reaction is 8.34. So what that also means is that the larger the PKS, the smaller amount of the ions that can get dissolved into the water, right? So similarly for this reaction here, since it's dissolving into one aluminum ion and three hydroxide ions. So if we write out the solubility products, so that's going to be the concentration of the aluminum ion multiplied by the OH ion to the power of 3, right? because it's basically determined by the coefficients before these reactants or products. So here you have 3 in front of OH. So that's why here you put 3 in the order here. So you can find that this KSP here is further lower, right? So if we write this out, PKS, that's going to be 32.9, right? So similarly, we defined a equilibrium constant for the acid-base equilibrium. So what happens is HA, which is an acid, can get dissolved into the the hydrogen ions and also the anion, right? So for example, if you have hydrochloric acid, it's going to be get dissolved into proton ions and the chloride, right? So similarly for the sulfuric acid, right, you can have this dissociation. So we can also define this equilibrium constant, let's say the Ka here. So similar to the solubility product, the larger the Ka value, the more it dissociates, right? The smaller the value, the less it dissociates. So we can also define this parameter pK here. So we have the pKa, right? So we found that for the hydrochloric acid, it has a value of -3, which means that almost all of them get dissociated, which means that this acid is very strong. But if we have a pKa of, let's say, 6 or 8, right, or further larger, let's say 30, 20, further larger, let's say, then it means that it's a weaker acid, right? So that's why the carbonic acid or the bicarbonate ions, they are weaker acids, okay? So we can use this concept of the pKa onto water because water is basically a hydrogen connected with an OH, right? So theoretically, water can get dissociated into a hydrogen or proton ion and an OH ion, okay? So we can similarly define this equilibrium constant. Let's say Kw equal to the concentration of hydrogen, concentration of hydroxide, divided by the concentration of water. So as we recall, for pure solid, pure liquid, this term should be regarded as 1. Okay, so that's why we have this equilibrium constant written as H multiplied by OH. Okay, further, people found that for this equilibrium constant, under normal temperature, normal pressure, it's just 10 to the -14, right? So again, we use this concept of the P here, okay? So we defined a parameter that's called pH, okay? pH is just the negative of log 10 of the hydrogen concentration, right? So based on this similar definition, we can define a pOH, which is negative log 10 of the OH ion concentration. So we can further apply this operator on both sides of the equation, right? So we have basically, let's say we take the log 10 first, okay? So log 10 of H multiplied by OH equal to -14, right? And then the product term in this log is dissociated into the addition or the sum, right? So we have negative of log 10 hydrogen concentration minus log 10 of the OH ion concentration is equal to 14. So what this means is that pH plus pOH is equal to 14. Okay, so this is basically a derivation of the relationship between pH and pOH. Further, we know that for pure water, the concentration of hydrogen should be equal to the concentration of the OH ions, right? So that's why if these two are the same, then pH plus pOH, or pH should be equal to pOH. Okay, so this is for pure water that doesn't have any ions inside, right? So further, by combining these two, we have pH equal to 7. which means that for pure water, for neutral water, the pH is always 7, right? I think you did the lab session of last week. So you're using some paper or pH paper to test out what is the pH value, right? For neutral water, the pH should be equal to 7. So this is basically the contents that we went through for our last class, okay? So the pH is a very important concept because we use, I mean, let's say for very acidic or very base conditions, no living organisms can stay in those environments, right? So for human beings, we want to drink water that is within the moderate range of the pH, right? But it turns out that for a lot of the uh, common objects or common things that we use, they range in a very large range of the pH. So here, I'm giving some more examples here. So as you can see, for human beings, our blood has a pH of around 7.4, which is kind of neutral, right? But for, let's say, for milk or urine or saliva, they're a little bit acidic. So further, black coffee, acidic, right? Sometimes you can taste it, right? So for juice or soda, they're more acidic. So for example, for the lemon juice, it's actually a pretty strong acid, right? Further, for the battery acid, we're using hydrochloric acid. This is a strong acid. Okay, so this is on the acidic side. And if you look at on the basic side, right? So the seawater or the ocean water has a pH of 8, which means that it contains more OH than the proton ions, right? So for baking soda or ammonia solution, there's stronger base, right? And then for bleaches or liquid drink cleaner, they're very strong base. So that's why we have to worry about the pH because for human beings, we're generating a lot of waste, right, into the water system. So if we do not tune our pH, tune the pH of the wastewater, and directly discharge them into the river water or let's say the lake, then a lot of living organisms might get killed, right? So for example, if we directly drain these bleaches or drain these liquid drain cleaner into the wastewater stream, then that's going to cause a disaster for some living organisms there. So that's why for wastewater treatment, we always need to know what is the pH before we discharge them. And accordingly, we need to bring in or add in some chemicals to tune the pH, right? To process the pH before we discharge them. So let's do a quick quiz here, since we already know the concept of the pH. So based on these values, so what is going to be the hydrogen ion or the OH ion concentration for the lemon juice? Okay, so let's spend some time to go over this question. Let me launch this pool here. Okay. So I'll give it maybe 30 more seconds, okay? Okay, I'll finish it here. So this time, before we show the results, let's just quickly go over this calculation, all right? So we're looking for lemon juice. So by looking at this table here, so we know that lemon juice has a pH of 2, right? So now let's think back on the definition of the parameter P. Okay, so P of a parameter, let's say P of A is equal to negative log 10 of A. Okay, so this is a definition, right? So pH, therefore, is negative of log 10, the hydrogen concentration, right? So if we have a pH value equal to 2, then what that means is log 10 of H is equal to negative 2, okay? So further, based on the definition of log, it should be 10 to the negative 2, okay? So which is 0.01, all right, 0.01 M. So basically here we need to plug in with the unit of M, okay, or mole per liter. So this is directly according to the definition of the H and the pH here. All right. So further, we know that the water constant, which is the product of the hydrogen ion and the OH ion, that's 10 to the negative 14, right? So this is always a constant. So if we have the hydrogen concentration is equal to 0.01, then the OH concentration is 10 to the negative 12. Okay, so does this make sense? So basically, based on the pH value, we can tell what is the concentration of the hydrogen ions or proton ions. And then further, based on the water constant, right, we can calculate what is the concentration of OH ions. Okay, so now I'll share the results. So actually, I think most of you guys chose the third option, which is incorrect here, okay? So with a pH value of 2, then the concentration should be 10 to the negative 2. It doesn't have a basically any value before this this concentration here, all right? So to just make sure that you guys understand this, I'll just relaunch this quiz, okay? Let's see whether you can get the correct answer this time. Okay, we'll just stop here. So I think this time all of you get the correct answer. Okay, so so we can do a similar calculation. So as you can see, I have the follow-up question. So what is the hydrogen ion and the OH ion concentration for seawater? Okay, so we know that the seawater has a pH of 8, right? So then, since we have this relationship, then pH is basically negative log 10 of the hydrogen ion concentration is equal to 8, okay? So what this means is that the hydrogen ion concentration is equal to 10 to the negative 8 M, okay? So this is the hydrogen ion concentration. So we have the water constant, Kw, is equal to hydrogen ion concentration multiplied by OH ion concentration is equal to 10 to the negative 14, okay? So if we already have the hydrogen ion concentration, which is negative 10 to the negative 8, right? Then the OH ion concentration is 10 to the negative 6, okay? It's just 14 minus 8, right? It's 10 to the negative 6 M, okay? So this is how we convert the pH values into the concentration of hydrogen ions and OH ions. I hope you're getting a little bit clear on this problem here. So you also get some practice for this homework one. I think there are a few questions related to this concept. So regarding your first lab session, I think you did some measurements of the pH values, right? So we have the Limtus paper or the pH paper to directly give us an indication of what is a pH for a lot of things that we use in our daily life, right? But the limitation for this limitance paper is that it doesn't give us accurate answers, right? It cannot tell the pH difference of something like 6.8 and 7.4, right? So they're all going to show up somewhere in this color, right? But it doesn't tell you what is the exact concentration of the ions. And compared to the limitance paper, we have more accurate measurements, like the pH probe. So I think this one is very accurate. It has 3 digits after this main value here. So this is going to be a more accurate way determining the pH values. Of course, for these instruments, they're going to be more expensive and also more difficult to use compared to these pH papers. Okay. So that's it about the acid-base equilibria. So we introduced quite a lot about the pH or the definition of the pH. So as I mentioned, for equilibrium, there are mainly 3 applications, right? So we went over the first one is the solubility product. Right, the second one is the acid-base equilibrium or equilibria, okay? So the third one is the one that we're going to introduce here. This is the gas-liquid equilibria. Okay, so the gas-liquid equilibria, you can think of it as a process. Let's say we have a container or we have a bottle, okay? So it has some water inside or some solution inside, okay? So now let's think of a process where you inject any type of gas, let's say oxygen or nitrogen, or let's say even helium, okay, which is an inert gas, okay? So for example, let's inject helium into this bottle here, and then we cap it, okay? So what's going to happen is that these helium molecules, although they're going to exist in the gas phase, so some of them will also get dissolved into the water or dissolved into this solution, okay? So this is what happens in the beginning. But then later on, we're going to construct an equilibrium, which means that the helium that's dissolved in the water are also going to get re-evaporated into the gas phase, okay? So basically, this equilibrium means that the flux of these gas going into the liquid is going to be equal to the flux of the helium coming out, okay? So for this equilibrium process, we have the Henry's law to basically determine what is the concentration of the gas related to the pressure of the gas in the gas phase, okay? So basically, what this means is that if you know what is the pressure of the helium in the gas phase, then you can know what is the concentration in the liquid phase, or the vice versa. If you know the concentration of helium in the liquid phase, then you can calculate what is the concentration of gas or what is the pressure in the gas phase, okay? So this is dictated by the Henry's law. So the Henry's law is actually quite straightforward. So what happens is the concentration of the gas species is actually linearly correlated with the pressure in the gas phase, okay? And they're related by this Kh here, which is called the Henry's constant, okay? So in this equation here, the C has the unit of M, okay? As we mentioned, M just means mole per liter, right? So this is concentration in the liquid phase. The P here has the unit of atmosphere, okay? So because of that, then the unit of Kh is going to be M per atmosphere, okay? So for example, for carbon dioxide system, so if we have the, let's say instead of injecting helium, let's put in carbon dioxide, okay? So this is basically the process where people make soda, right? That's why you have a lot of carbon dioxide in the liquid there, whenever you pop up the soda there, okay? So for carbon dioxide, people determine that this Kh, the Henry's constant, is equal to 10 to the negative 1.47 m per atmosphere. Okay, so we're trying to match this unit. All right. So what this means is that, let's say if we know the carbon dioxide pressure in the gas phase, let's say 0.5 atmosphere, then we can calculate what is carbon dioxide concentration in the liquid. We just multiply this Henry's constant by the pressure, right? We can calculate what is concentration within the water. Or let's say if this concentration or if this pressure is 0.00001 atmosphere, then accordingly we can calculate what is carbon dioxide concentration in the water. So similarly, let's say if the carbon dioxide concentration is 1 m, okay, so we can back calculate what is the partial pressure, what is the gas pressure of the carbon dioxide. Okay, so this is how we use it. But why do we learn it, right? So why is it important? So a very, very important application of this Henry's law or Henry's constant is the global climate change. Okay, so we know that the climate change is a sure thing, right? It's mainly because of the greenhouse gas species, right? And more specifically, carbon dioxide contribute a lot to this greenhouse gas species. So you can think of it as, let's say this is our Earth, right? So we have the continents of Asia, Africa, Europe, North America, South America, and Australia, right? Then basically this is our Earth, right? And we have the atmosphere that's surrounding this Earth, right? And there are some greenhouse gas species. So what happens is these greenhouse gas species is just going to, they're just going to act as a quilt, right? We have the solar radiation that's coming in to warm up the climate, warm up the temperature of the Earth. But because of these greenhouse gas species, the thermal energy, they're not going to be emitted back into the universe quite easily, okay? A fraction of them will just keep inside the atmosphere, which is causing the temperature to rise up. Okay, so this is why people also call it global warming, but we also need to know that warming is not a let's say a direct thing. So if you still measure the average temperature all around the Earth, the temperature is definitely warming up. But for regional scales, the regional climate or the regional weather, it might be different. Compared to this trend. Okay, so that's why people also use the climate change, because we're definitely seeing a lot of the locations, the climate is has been fluctuating quite a lot. So a more direct way of seeing this effect of the carbon dioxide is from this curve. Okay, so people also call this as a Keeling curve. So Keeling is the person who did this measurement. So what he did was he started to measure the carbon dioxide concentration in Hawaii. So basically it's in the middle of the Pacific Ocean, right? So in that way, it's not affected by the coal-fired power plants or from the continents. So what he found is that the carbon dioxide concentration has been rising from around 315 around 1960s all the way until now, around 410. Okay, so this is just the data 3 days ago. Okay, so you can see that within this 60 years, let's say that this is 310. Okay, so within this 60 years, we rise up the carbon dioxide concentration by 100 ppm. So 100 ppm may not sound very alarming, or you don't have a specific understanding of this concentration, but let's just compare the background concentration. Okay, so background concentration is 310 ppm. So what that means is that within this 60 years, we rise up our carbon dioxide concentration by almost 33%, okay, which is basically a very, very significant increase, right? So this is not even acceptable. So we're just dumping in so much of carbon dioxide. So why is it increasing this suddenly? Okay, why is it not like smoothly or peacefully increasing? So on one hand, it's definitely because of the human emission, right? So one thing is the emission. So we're definitely emitting more due to the industrialization. But on the other hand, it's because of the Henry's constant. It's because for the carbon dioxide, it has a very, very small Henry's constant. Okay, so now let's imagine um, the situation where we dump in this carbon dioxide into this bottle again. Okay, so this is kind of simulating the process where the coal-fired power plants inject tons of carbon dioxide over our Earth. All right, so what happens is, let's say if we put 1 kilogram of the carbon dioxide into this bottle, then according to the Henry's law, then some fraction of the carbon dioxide are going to get dissolved into the water, right? So if we have a very large Henry's constant, okay, so I'll just write it here. If we have a very large KH, so what that means is we're going to have a higher concentration of carbon dioxide, right, in the water, okay? And also compared to that, we are going to have a smaller value of the carbon dioxide pressure in the gas. So what this means is that if it has a large KH, then more CO2 are going to get dissolved. Okay, but if you have a very small KH, then only a tiny fraction can get dissolved, right? So what that means is you have a very large value of the P gas, right? But since you have a very small value of the Henry's constant, then only a tiny fraction can get dissolved. And that is actually the case for carbon dioxide. It cannot get dissolved in water very significantly. So that's why almost all of the carbon dioxide, or at least not all of them, but a large fraction of them are going to stay in the atmosphere and they'll cause this greenhouse gas effect. Okay, so why that kind of explain why this process or why this equilibrium is important. And of course, in industry, we all know that soda making needs carbon dioxide, right? So that's what also determine how much of the gas you can dissolve in the water. All right. So that's all for the equilibrium or the chemical equilibrium. All right. So we can give a application of this equilibrium process. So I think last lab session, you also learned the buffer system. So the buffer is defined as a solution that can resist a large pH change, okay, when the acid is added into the water or it's being diluted. So the reason why why this buffer can work in that way is you can kind of understand it by doing these calculations. Okay, so we can do 3 calculations to get an understanding of it. So what will be the pH value if you add HCl or hydrochloric acid into the water and then make its concentration to be 0.1 m? Okay, so we know that if the concentration of hydrochloric acid is 0.1, then we know that the hydrogen ion concentration is also going to be 0.1, right? So then you know that based on the definition of pH, right? So pH is negative log 10 of the hydrogen ion concentration. So that's going to be 1. Okay, so if you add this amount of hydrochloric acid, then the pH is going to be very low. It's a strong acid. All right. So then what will be the concentration or what will be the result if you have 0.1 m of sodium carbonate in the water? Okay. So if you have sodium carbonate, then we know that the hydrogen ion can react with the carbonate ion. So what happens is sodium carbonate react with hydrochloric acid at 1-to-1 ratio because both of them are at 0.1 m, right? So they can form sodium chloride and then sodium bicarbonate. So you see the difference is that for this pure water, you have a lot of free or excess hydrogen ions. But for this second condition here, you don't have the free hydrogen ions, right? Everything is still fixed into this chemical here. So you don't have these free hydrogen ions, which is going to reduce the pH value. So that's why if the solution has these carbonate ions, then they can reduce or they can resist this large change of pH. Okay, so then we can ask question, if you further add in add in 0.1 m, which makes it 0.2 m in total, what will be the pH? So what you can find is that basically if we add 0.2 m, then that means you're reacting with two numbers of the hydrochloric acid, right? And then you're going to get two sodium chloride, and then you're going to have carbonic acid. Okay, so now we know that carbonic acid is a weak acid, right? So it's not going to generate as much hydrogen ions compared to the hydrochloric acid. So that's why you can also further reduce the change of the pH. So basically you're changing this strong acid into a weaker acid. Okay, so this is basically why we call this carbonate species as the buffer species, right? You can form a buffer solution. Basically, if you pour in a lot of acid in there, it's going to resist the change of the acid. So more detailedly, if you look at the chemical reactions, what happens is the carbonic acid, they can get dissociated into hydrogen ion and the bicarbonate ion. So this is called bicarbonate. Okay, so the bicarbonate ion can further get dissociated into the hydrogen ion and the carbonate ion. Okay, so basically this reaction is reversible. These reactions are reversible. So when we're discussing this process, right, when we're discussing this process, what happens is we're letting the hydrogen ions to react with the carbonate ions to go this way, to form bicarbonate ions. So that resists the change of the pH. So further, if we add 0.1 m more of the hydrochloric acid, we further let it go this way, right? So to make them carbonic acid, right? So that's a weak acid. So now if I ask you, how many hydrogens can a carbonate ion react with, right? So how many hydrogen ions? Okay, let me write out this question. How many hydrogen ions can a carbonate ion react with? So the answer is going to be 2, right? Because it can first react with one hydrogen ion to form bicarbonate ion, and then the bicarbonate ion can further react with hydrogen to form a carbonic acid. Okay, so similarly, if I ask you how many hydrogen ions can the bicarbonate ion react with, so that's going to be 1, because you can only react with one hydrogen ion to form carbonic acid. Okay, so this concept is going to be useful when we discuss the alkalinity, which is also a topic for your lab experiments. Okay, so then you may have the question. So it seems that we have quite many species that contains this carbon, right? So if I label them out, you have the carbonic acid, you have the bicarbonate ion, and you can have the carbonate ion. So can they all exist at the same time, right? So can they coexist? The answer is no, okay? So only 2 of them can exist at the same time. So what that means is, so here I'm showing this diagram that's called the speciation diagram, which basically shows what are the fractions of these carbonate, bicarbonate, or carbonic acid species. What are their concentrations or fractions under different pH conditions? So what you can see is that under a wide range of pH, let's say from around 3.5 to all the way around 13, you have this conversion of the carbonic acid, bicarbonate, or carbonate ions. Okay, but when the pH is below 8.4, okay, so only carbonic acid and bicarbonate ions can coexist. Okay, so when the pH is larger than 8.4, only bicarbonate ions and carbonate ions are going to exist. Okay, so there's no way that basically these two can exist. And actually this makes sense because just think about it. So if we have a carbonic acid and a carbonate ion, they're going to react with each other to form two bicarbonate ions, right? So that's why they cannot coexist at the same time. So actually this diagram is quite helpful because it also tells us what is the concentration of these ionic species under different pH. So let's say if we have a solution that has a pH of 6, okay, and we know that there are some carbonic acid and some bicarbonate ions, then we can use this table to find that actually the carbonic acid is going to have a fraction or the number fraction of around 65%, while the bicarbonate ions are going to have a fraction of around 35%. Okay, so let's say if you have 1 mole per liter of carbon atoms in this solution, then you know that 65% of these carbon exist in the carbonic acid, and then 35 of them exist in the bicarbonate. And similarly in here, let's say if you know the pH is 11, then you know that around 85% are in carbonate ions and 15% are in bicarbonate ions. Okay, so this is why this speciation diagram is quite important in helping us know what is the composition of a buffer, right? So if you have a buffer solution, now you can just measure the pH. If you know the pH, then you know the concentration of all of these ions, okay? So we can also use this concept to do some interesting questions or interesting calculations. So for example, what is the natural pH of rainwater? Okay, so if we know this speciation diagram, or if you know these reactions. So for rainwater, for a droplet, what happens is there are a lot of carbon dioxide surrounding this drop of water, right? So we know that based on the gas-liquid equilibrium, we can use the Henry's constant, right? So basically C is going to be equal to KH multiplied by P, right? By plugging them in, it's going to be this, right? So we know the Henry's constant for the carbon dioxide. So if we know the concentration or the pressure of the carbon dioxide, then we can calculate what is the concentration of carbon dioxide in water, right? So the form of the carbon dioxide in water is just the carbonic acid, okay? Because it's just carbon dioxide reacting with water to form carbonic acid, okay? So based on that, we can calculate that the carbonic acid concentration can be calculated with this equation here. You know the Henry's constant, right, for carbon dioxide, and then assume that the carbon dioxide pressure has this value. Okay, so you can find out that the final answer is around 10 to the negative 5 m. Okay, and then we know this chemical equilibrium, this acid-base equilibrium, right? It has a equilibrium constant of 10 to the negative 6.35. So what that means is Ka1 for this reaction is going to be the concentration of hydrogen ions and the concentration of bicarbonate ions divided by the concentration of carbonic acid is equal to 10 to the negative 6.35. Okay, so in this equation, what do we know? We know the concentration of carbonic acid, right? And then how do we calculate the pH? So the pH is just the concentration. It's just the concentration of the hydrogen ions, right? So basically we're trying to solve for this one. And then further based on this reaction here, we know that the hydrogen ions and the bicarbonate ions are forming at a 1-to-1 ratio, right? So these two should be equal to each other. So the hydrogen ion concentration is equal to the bicarbonate ion concentration. All right. So then we can simplify this equation so that it's hydrogen ion concentration to the power of 2 divided by the carbonic acid concentration. Okay. We have this value here. We can just directly take the square root to calculate the hydrogen ion concentration, right? That turns out to be 10 to the negative 11.35, and this is the square of the hydrogen ion concentration. So if we take the square root, that's 10 to the negative 5.7, right? So the pH is equal to 5.7, which is acidic, all right? So that's why the raindrop, even without the acid rain formation, is actually quite acidic because of the carbon dioxide in the atmosphere, okay? So finally, it's the alkalinity. So I think you also did some experiments with the alkalinity. So the alkalinity originates from the word alkali or alkali. It basically determines or it describes how much acid or how much hydrogen ions can this solution react with. Okay, so the more alkalinity or the higher the alkalinity, the more hydrogen ions it can react with. Okay, so formally it's defined as the acid neutralizing capability. Okay, so actually it's just calculating how much hydrogen ions it can react with. Okay, so if we assume that the water is only composed of the carbonate species, okay, so then we can quite easily write them out, right? So if it contains carbonate species, then we know that it has carbonate ions, bicarbonate ions, OH ions, and hydrogen ions, right? As we mentioned earlier, each one of the carbon ion can react with 2 hydrogen ion, right? Each one of the bicarbonate ion can react with 1 um, hydrogen ion. So each OH ion can react with 1 hydrogen ion. And the existing hydrogen ion in the water, they cannot react anymore, but we have to subtract them because the existing hydrogen ion can already react with these species, right? So that's why when we list out the equation, the alkalinity is just the concentration of bicarbonate plus 2 multiplied by the carbonate ion plus hydrogen ion and minus plus the OH ion and minus the hydrogen ion. Okay, so the final answer is shown in mole per liter, right? Or people also use the unit of equivalent per liter. Okay, and then basically whenever you see this equivalent per liter, that just means mole per liter. Okay, so it's just a convention of showing these units. So we can also convert mole per milli to millimole. So that's 1,000 millimole or 1,000 milli equivalent per liter. Okay. So then based on this definition, what is the alkalinity of pure water? So pure water doesn't have these carbonate species. They just have OH and hydrogen ions, right? So based on that, you can know the alkalinity of pure water is just 0. So here I have a simple example problem here. So since we don't have the time to discuss this question, maybe you can go over this off the class. I think you also have some related questions in your homework. This is actually quite straightforward to calculate what is the alkalinity. And then one thing is that people also convert this into the mass concentration of the calcium carbonate. This is kind of like an analogy for your calculation. So please go over these 2 slides or these remaining 3 slides of the class, and that may be helpful for some of the homework questions. And of course, in our next class, we're going to finish this up. Okay, so that's all for this class. Let me know if you have any questions.